So we've already said quite a bit about the concept of homotopy in topology. Two continuous maps are homotopic if there's a kind of one parameter family of maps that interpolate between them. Now we want to explain a concept in the theory of chain complexes that turns out to be quite closely analogous to that. And that's called chain homotopy. So the idea is we've got two chain complexes, A and A prime, and two chain maps, F and G, from A to A prime. Remember what it means for these to be chain maps. It means that DF is FD and also DG is GD. So a chain homotopy between F and G is a system of maps SR from AR to A prime R plus 1 with certain properties. So we have the picture is like this over here. So we've got our chain complex A over here with a differential dr from AR down to AR minus 1. And we've got AR here, AR plus 1 here, and differential there, but we're not showing it in this picture. And then over the other side, we've got our chain complex A prime with an A prime R plus 1, A prime R, and then A prime R minus 1 would be down here. And so this S increases degrees by 1. So we've got an SR from AR going up to A prime R plus 1, and the SR minus 1 going from AR minus 1 up to A prime R. And the condition for it to be a chain homotopy was like this, that if we look at the difference between these two maps, G and F, look at GR minus FR, it should be equal to DS plus SD, okay? Or more precisely, we do this SR and then follow it by a DR plus 1 on the A prime. That's our first term here. And the second term, instead of doing the S and then the D, we do the DR down to AR minus 1, and then we do the SR minus 1 going up here. So in other words, the difference between these two maps here in the middle should be the same as the sum of this map and this map. So we've written it here with all the indices and everything, but we could just say it more briefly as G minus F is DS plus SD. The first thing to note is that this is actually an equivalence relation on chain maps. So what does it mean to be an equivalence relation? Well, it has to be reflexive, symmetric, and transitive. So reflexivity, F has to be chain homotopy to itself. Okay, so in other words, it has to be a chain homotopy from F to itself, and there is. We just take each SR to be equal to 0, right? Then F minus F is 0, which is D0 plus 0D. That's all fine. Then the relation is supposed to be symmetric. So if F is chain homotopic to G, then G is supposed to also be chain homotopic to F, and that's easy to do, right? If S is a chain homotopy from F to G, so G minus F is DS plus SD. Then we just replace S by minus S, and we get a chain homotopy the other way around from G to F. Finally, it has to be transitive. So if we've got a chain homotopy S from F to G, and then also a chain homotopy T from G to H, then we need to show that F is chain homotopic to H. So we need to produce a chain homotopy from F to H, and we just need to use S plus T. Okay, so let's just check that works. So it's supposed to be, the claim is going to be that D composed with S plus T composed with D, that's supposed to be equal to H minus F. So we just work it out. Firstly, we can just expand and regroup the terms. So here we've got a DS, and there we've got an SD, so we've got DS plus SD, and then here we've got a DT term and a TD term, so we've got DT plus TD. But now DS plus SD, by assumption, we're assuming that S is a chain homotopy from F to G, so that this DS plus SG is G minus F, and then the DT plus TD, well, T we're assuming is a chain homotopy from G to H, so DT plus TD is H minus G, and then here the plus G here and the minus G here, there, they cancel out. We're just left with H minus F. So we conclude that S plus T is a chain homotopy from F to H. So this is indeed a transitive relation as expected. So it's an equivalence relation altogether. So a key point about chain homotopy is you've got two chain maps that are chain homotopic to each other, then they give us the same effect in homology. Right? So here, let's say that in more detail. You've got A and A prime are chain complexes. F and G are chain maps, again, that are both going from A star to A prime star. And we're assuming that they're chain homotopic in the sense that we had on the last slide. And the claim is that the induced map F star, go from H star to H star A to H star A prime, is the same as the induced map G star from H star A to H star A prime. And that's not very hard to prove. So we're saying that F and G are chain homotopic. That means that there exists a chain homotopy between them. So G minus F is ds plus SD for this map S. Okay, so now let's consider an element in the homology of A. So that can be represented as square bracket Z for some cycle. Remember what it means for Z to be a cycle. So Z is an element of AR with dz equals 0. Okay. So let's look at GZ minus FZ. Okay, so because G minus F is ds plus SD, so it's dSZ plus SDZ. But but remember, Z is a cycle, so dz is 0. So this second term here, we can ignore that. That goes away. And then we can just move the FZ over to the right-hand side. So we've got GZ is FZ plus DSZ. Okay. But the key point is that this is D of something, so it's a boundary. It's an element of BRA prime. Okay, so that's saying that the coset of GZ and the coset of FZ with respect to BRA prime, those are the same. Or in other words, in the kind of normal square bracket notation, square bracket GZ is the same as square bracket FZ in HRA prime. But remember the way this F lower star works. F lower star applied to a homology class, you just put the F on the inside. So here we're saying that GZ, G star Z is the same as F star Z. And Z was an arbitrary element of the homology HRA, so we conclude that F star is the same as G star.